Thank you. So last time we introduced the entropy pairs and I pairs, more generally I tuples. So we mentioned that basically they are really the same thing. Pairs. Yeah. So what you call that? The setting is that actually gamma acting on x, where gamma is mutable and x is compact returnable. Yeah. I pair simply just means that so this is entropy pair. Means that if you take any closed neighborhoods of these points so that they are disjoint, then if you look at it would be the complement of these guys, so it's open cover of x. The entropy pair simply just means that this always has positive for entropy. Well, I pair means that for the top for the pair of AB1, it has positive independence density. Where this means the infimum over f, so that we look at the size of k. So k is contained in f, and these are independence set for a. And here f ranges over non-amplifying subsets of the group. And now for this fact, one direction is actually very easy to show. If you want to see the right hand side is contained in the left, that's the easy part. So in general, it's what you can see here. So if we have more generally, if we have several sets A1, A2, so A1, AK, so closed subsets of X, and pairwise disjoint. Then one can look at the cover, the complement of these guys. So this is still a finite open cover, just like this situation here. Is that I'm looking at more generally K here. Yeah. And then what we can say is that the entropy of it will be actually at least the independence density times logarithm of k. Okay, so here A is this type of sets. The reason is that if we look at the joining of such things, we try to calculate the entropy. We're looking at these guys and look at the family of open sets inside of it, which is required to cover the whole X. Look at the smallest number there. Yeah. Now, what we notice is that if you take any element here, so it will be of the form AGA. So S, maybe put the sigma S complement. So one element in this open cover will be like this. Okay. But what does this mean? This means that if for each S you choose one of them, then look at the complement. But this will cover at most open. Maybe I see it this way. So this, first of all, this would be actually at least I take one open independence set there first. So I take let's say Kn independence set for A with that the size will actually give us this largest hold on, somewhere I wrote it wrong, so this will be this this should be the density. So, and here I should take the maximal size and divide it by the size of f. Okay. So we take one such that this Kn here divided by size of f1 is at least this density. Then I can change f1 to Kn. That will make it the cover actually to be coarser because we are taking the joining for pure open covers. Okay, so this will be this inside of Kn. Yeah. Now when we look at this one can see that well, now each open set here is of this form, and for each S we're taking one place to look at the complement, and for every such sigma actually you get at least 1 point in the in this so for every S, for every S, if I want to say specify one point to be inside of this one or inside of another one, you always get 1 point. Okay. But then this guy, this choice actually will cover actually at each S cover at actually exactly k minus 1 minus points. Put them together. Okay, so this will contain exactly just k minus 1 to the size of Kn many points. Many x phi. So x phi here, this is that x phi would be inside of the intersection of S inverse. For phi n is the map from Kn into 1, 2. We can find such points because of the definition of independent set. That's exactly the definition. Okay. And each open set here contains actually exactly just the k minus 1 to the size of Kn many such points. But how many points here do we have here? In total, this number here is just the k to the size of Kn. K minus 1 to the size of Kn. Many such. It's fine. So you see that we need how many open sets here to cover the whole X? At least you need those points, those open sets to cover all these X phi's. But then you see that this will be actually at least the total number here, that is k to the size of Kn, divided by k minus 1 to the size of Kn. Then this is at least k divided by k minus 1. Because this is bigger than 1, so we can make actually k to be slightly smaller. Replace it by the density here times F1. Maybe I just write it here. This will be k divided by k minus 1. The density times the size of Fn. Now we take a logarithm both sides, divided by size of Fn. We see that we get this, no, not this is quite correct. This will be k divided by k minus 1. But then that will be part. So that is the easy part. From the independence on this right hand side, you can easily get that the entropy is pi. Questions? Now for the other direction, that is the main the difficult part, is that one needs to use either Gödel theory or actually to use combinatorics to get it. So here we'll see the combinatoric facts. So first of all, let's look at some notation here. So we look at the k at least 2, and the empty finite set. And we look at the set 1, 0, and 2k to the z. Okay, so this will be really just products of 0, 1, and 2k. This is finite set. Okay. Yeah. Then we try to look at certain covers of it. So W will be the cover of this set. Consisting of subsets of the form that is at each coordinate we take out one point and look at the complement. Where this IZ will be actually between 1 and k. So at each coordinate z, I take out one point here, look at the complement, then look at look at complement and look at the product. Okay. But for this point where we take out, it cannot be 0. So only allowed that you take out one point from 1, 2 until k. Then for S, if you have a subset here of this set, of this product set, then we just write n sub S to be basically pretty much just like the definition in the entropy here. You look at the minimal number of sets of this form to cover this set S. Now we can state the combinatorial lemma.
Could you please once again just read? So you wrote F and S. So what's Fn here?
Fn here. Yeah, I should say that Fn is the left further sequence.
Okay.
So let me. I should say it here. So F1 left for the sequence of gamma, so that means SF1 symmetric difference with F1 divided by the size of F1 goes to 0, Sn goes to infinity for every S in gamma. And the entropy is defined as this guy taking a logarithm divided by, let me write it here. So this is defined as limit right. Now we can state the combinatorial lemma. So this says that let k at least 2 and be positive. Then there exists, say, constant depending only on k and b, such that for any finite set z and s in 0, 1 until k to the z, so s will be just like this situation here, with the mass is at least k to the b times the size of z. So what this means is that basically with x, k, and b, we're going to eventually let z to become very large. So z actually will play the role of basically fn here, become very large. What this really means is that this number here actually grows exponentially. That's what it is talking about. Because we will not specify how large is b. B, you could think of b as very, very small, very, very close to 0. For any such z and s, there exists j inside of z, such that the size of j is at least c times the size of z. So that means the density of j inside of z is positive, is fixed, it has this c as a lower bound. And s, when we restrict j, actually we'll get all the possible choices. So with restrict on j, this will be a bunch of maps from j to this set. Okay, well, basically, conclusion that we get everything, except that we don't really need 0. What we really care about is 1 until k. We're going to get 1 until k to the j. We get all such maps here. Questions? We'll see that in a minute. From this lemma, one can get the other direction of the equality here very easily. Okay. Maybe I just
Sorry. So in the previous definition, it says Fn, but I don't understand because S is a subset of the double power set.
yeah.
So why is there an Fn there?
This is my conclusion. It's 4.
It's not 4. It's 4. So it's not Fn.
I was exactly confused.
Okay. Yeah. Okay. Before.
Above NS, we were confused. Above NS. This is 4S in
Third line.
Yeah, it's
Before S.
Before
S. Before S.
Oh, this is 4.
I thought it was Fn.
Sorry. Okay, maybe I will show you first how to use this lemma to finish the proof of the theorem. Then I will say a little bit about history of the lemma. Yeah. All right.
Sorry. So, a different question. So is it correct to think that intuitively the lemma says that if the covering number is big, then there is an independent set with both big? Well, there are some constants there, but
Yeah, this is really saying that if the cover number is growing exponentially, then you get, this is really, J is kind of an independent set. You get an independent set with infinity, as you see here. So to use it to prove the theorem, the K here is that I will just write down one lemma here. So it will basically be setting up like this. So we let run here K closed pairwise disjoint, and U to be the complement of them. Then the entropy is positive if and only if you get that this tuple K here has independence density in positive. Okay, so here is K is set to these two. Yeah. So once we prove for this lemma, so that this lemma implies the theorem. Okay, implies the other direction. Actually, one direction is just already written down here. So this direction done already. That is exactly the argument here. One does not need the combinatorics. But in any case, this lemma implies the theorem. Actually, just we need the case k equal to 2. That's exactly what it's saying. And now for the other direction, we're going to use the combinatorial lemma. And let me explain how to really use it. But you can already see that the formulation here is somehow related, right? Here I was talking about the covariant number. Here is kind of like an independence set. Yeah, just here, actually one has dynamics. There is no dynamics there. Okay. So for the other direction, in this direction, for the lemma, what you do is the following. I think. Yeah. So we consider a map for each triangle for each n here, for each full set. From x to 0, 1 to k to the Fn. So we're going to take that z to be just Fn. So this would be that we send each point to what? To look at each s. We're going to assign some number here. What you do is look at the image of x under the s and look at where it's sitting. It's inside of one of these AJs or actually in the complement. So if Sx is inside of, I should say S, so S will be inside of Fn. So if Sx is actually inside of these guys, then it's clear what we should do here. We just take the value j here. But if it's not, otherwise, what happens is that this x is actually inside for the complement of all these AJs together. Yeah, then we just put it as 0. That's why we need 0 here. Okay. Yeah. Then you see that if you want to cover the whole X using elements in here, that's basically the same as trying to cover the image of these guys using the sets of this form. That's exactly the same thing. And the image of X, so we're going to take that S there to be this image. This is exactly the same as a number for this open cup. So what we get is that when n is not, we know that here, but in the definition of entropy, we take a logarithm divided by size of Fn. This will convert it to the entropy of U. We're assuming it to be positive. So when n is not enough, we have that this number here. So this would be actually the same as this one. This will be at least e to the half the entropy times Fn. Yeah, so we're just saying that when we take a logarithm divided by the size of Fn, that will be at least half of the entropy because we are assuming that the entropy is positive. Okay. And when n is not enough, it's actually converging to this guy. So here, you just write k to the b to be this number. Okay. Then we already have k fixed, so you just simply use this equation to decide b. Then the combinatorial lemma tells us that there is this C, depending on K and B, but then it really just depends on K and this entropy here, such that when n is not, we get J inside of Fn with the Jn at least C times the size of Fn. And this phi x here, when you restrict to Jn, we get everything. But then this really just means that Jn actually is one independent set for the tuple. So this means that Jn is an independent set for E1 to Ek. But then we get that the independence density for A will be at least this number C here, and this one. Questions? What we're really saying is that you might think, even if you believe this is true, you might think that there are complicated dynamical reason behind it. Okay, but in fact, the fundamental essence is that it's really combinatorial. It has nothing to do with dynamics. So now let me get back to this lemma, combinatorial lemma here, to see a bit the history of it. So this is one line of research in combinatorics for things of this form. Let's go kind of like a similar. The origin actually started with a question of Erdős. So he asked the following question: if you have the infinite, so this means here I'm writing for the power set of Z. So you look at a bunch of subsets of Z, where Z is an infinite set. Then he asks whether actually you get a certain dichotomy. Okay. Either A is kind of small or A is actually kind of large. So they must either 1 or 2 hold. So one is that the case that A is kind of small. No, actually it's kind of large. So this is A large. The following, when N, there exists one J inside of Z. Infinite, but the size of it is exactly equal to N. Yeah. So only intersects with J, you get everything inside of J. For this, I mean that here this is a bunch of subsets of Z. So what we do is really take all the subsets inside of A, take an intersection with J. Then you get a bunch of subsets of J. So this becomes a bunch of subsets of J. So the condition here is that you get everything. The other situation is that A is kind of small. This is that there exists N and C, such that for any J in Z with so any subset of Z large enough, but infinite. One has that we look at A intersected with J. So that's defined here. So get a bunch of subsets in J. So restrict everything of A inside of J. Then here what you get is that it's kind of the opposite here is that this situation you get everything. Here you get a very, very few in the sense that actually has polynomial growth. So this will be at the most the size of J to the C. All right. So this is Erdős's question. Then it was answered affirmatively with our comparison Chanel. So there is Chanel. Two independently, they said that actually the answer is yes. This is true, okay? But they actually proved a much stronger statement. They showed exactly what happened when you take Z to be actually finite. So what they really showed is the following. So if Z cannot be finite, okay, and A is inside of within the power set of Z, bunch of subsets of Z, and you take some number integer here, M. Okay. Then you ask whether you can restrict to some subset of Z with the size N, so that when you restrict A to that guy, you get everything. Okay. Yeah, just like the situation here, whether you can do that. Okay. Then what it really showed is that there is a precise bound for that. So if the number of elements in A exceeds a certain number, then you can do it. Okay, but they found that the precisely the optimal number. Yeah. So if the size of A is at least the number of subsets of Z with cardinality smaller than M. Okay. So if you look at take A to be this guy, then of course you cannot get that some subset of J of Z with size M, and we restrict to J, you get everything, because there inside of it you just simply don't have any set with cardinality M at all, or at least M. Yeah. So then there is this J in Z with the size being M, and we restrict A to J, you get everything. So what they showed you that if you don't want this to happen, the largest size of A is exactly just this number. And this number you can write down easily, right? This is simply combinatorics. So this would be like M, and the size of Z, you choose J. Okay. Then you see that this is actually this is a polynomial of degree M in the variable of the size of Z. So this has polynomials. Questions? Then later, Kapowski and Muehlmann extended this to a slightly more general situation. So K2, this is simply just star. This they showed, they said the following. I guess I can still write a few lines here. If K is at least 2, and Z is like this, non-empty finite, and A is inside of 1 until K to the Z, and you still take some number M, such that the size of A is bigger than all the F in K to the Z, so that's F inverse of K. So number of place we get the value K, the largest guy here, is strictly smaller than M. Then you can find the J, so that on J you actually get everything. And A restricted to J, you get everything. This corresponds to the case that the K is simply just equal to 2. Here you usually write 0, 1 to the Z, but you can change it slightly, say it's a 1, 2, evaluate it as 1, 2, and that corresponds to exactly the situation here. Questions? Now, the Karpowski-Millman implies the following fact. This is very nice result in extreme combinatorics. You get the optimal number for this thing not to happen. Okay, but in real application, one does not need such a strong form. One just need, especially in dynamics, what you need is just in the case like they go to the size of they go to infinity. Yeah, just need some weaker asymptotic form. So this is the asymptotic form we usually used. So let's have these two and 1. Then maybe this C prime here, such that when the n natural number and s inside of 1 to k, here 1 to n, with the size of s at least k minus 1 lambda to the size of n. There exists j inside of 1 to n, such that the size of j is at least c times n. And when you restrict s to j, you get everything. This consequence of it, just because what you do is that you take this z to be this 1 until n. That's the final set, which is simply write as 1, 2 until n. Yeah. And the condition here really says that the size of s has exponential growth, and actually it's slightly stronger than that. This says that the base here is actually bigger than k minus 1, really says. Okay. Yeah, the conclusion is that you can find some j with this density, say, so that on j, when you restrict the s to j, you get everything. Yeah. But here, what we're seeing is that if you don't want this to happen, then the size of a here corresponds to this s here should be at most this number. Yeah, but you can compute it combinatorially very easily. You see that actually the number here actually is really smaller than this one. I mean, it possibly has exponential growth, but you won't get such a bigger number. Now you can say the relation between this combinatorial lemma and this one here. Yeah, this combinatorial lemma here easily implies this one. Just simply consider a situation that s, difference here is that the s here possibly also take value of 0. But here, s here does not take value of 0. So if you simply have s here, then you just put it here, then you get a conclusion. So this directly implies this one here. Using this lemma, you can also show that when the system has positive entropy, you get like IE pairs. In the case that the system has 0 dimension. Totally disconnected. Yeah, but when it has topology there, you cannot really get Clopin partitions, then you get trouble. Then you really do this way. And the proof of this combinatorial lemma is much more complicated than the proof here. The proof here is actually it's tricky, but to get one simple idea, then its proof is basically like 1 page. Here, the proof is not much longer. It's only 2 pages. But if you have ever experienced proving something combinatorial, you should know that in combinatorics, typically the proof is short, but you need to get the correct idea, and it's quite tricky usually. Yeah. So we're not going to get the proof here. Yeah, it's quite technical. I don't think you want to really use the proof at some other place situation. Okay, maybe now we take some break.
5 minutes, is that okay? Or, yeah, 5 minutes. Okay.
è stato si chiama allora guarda, io ho detto non la voglio guardare, cioè nel senso perché ho detto dopo te la faccio però devo dire la verità, tanto non
Sì, sì.
ho proprio capito da sé.
Sorry?
Per ora non sono interessata. Capì? Cioè, no, però cioè, non è che era veramente una sala, ovviamente tutte le case. No,
Zapewne mamy sytuację na uczelni. Cała kwestia się pod ksefę przygotowuje.
io sono nato per
I aktualnie jakby cała uczelnia
quello
jest...
alla fine ho scelto la carriera perché poi vabbè era complicato fare il quindi insomma mi è sempre rimasta la cosa.
Mają osoby, co były wprowadzone do kamienia i miały
Certo. Sì, sì.
listopada, czyli to był miesiąc po tym, jak już nie pracowałem.
L'anno ricominciato. No, no, infatti io ti volevo scrivere così ci potevamo andare a vedere.
3 lata etat badawczy. I złożyło przedłożenie i mu nie dali.
I mean, if you want.
Yeah, that's why want is actually yes.
You have.
Is this something I've been dreaming of the whole morning? Well,
Not really. But you have to, I guess.
Quindi va bene.
Did you really?
okay. Do the whole day.
So you want to talk today?
Sì, è vero, è vero, è vero.
Però mi ha ricordato quando avevo 11 anni che andavo al parco.
Sì, si vedrà.
To się pozatrudniali
Chcieli, żeby uczył jeszcze.
i w rozpisce godzin
Questo dalla legge.
układów dynamicznych, teorii ergodycznej. Została matematyka 1 na ceramice.
To jest takie Hanfeng.
I dostał wykład z idealnie też.
Devi fare 3 lezioni da un'ora.
Wiesz,
Mezza, me le devo ripetere tutte insieme. Il tempo,
że wcześniej, teraz jest na przykład Sorbonne. Wiesz, jakby to nie jest ponad na tym wydziałem, żeby kogoś na stanowisko badawcze, żeby mieć.
No, certo. Appunto, penso che alcune cose vedremo
Myślę, że połączenie tego,
improvvisare, però magari
tylko w jaki sposób.
una dimostrazione più nel dettaglio, se magari vedi che mi stanno seguendo le domande, altrimenti
Miesięcznym okresami wypowiedzenia. Już wcześniej zapytałem. Do nich powiedziałem, tak, że będziemy jedno.
I cavi di una volta.
sì, sì. Quindi sulle cose
Che trovi?
sugli strumenti che uno utilizza. Sì, no, sono d'accordo
Ti
con
dicono vai bene poi.
sono d'accordo, ma io sono sempre un po' più di questi ambiti. Molta specifiche.
No, żadnej dydaktyki nie ma nic, po prostu siedzi sobie w Krakowie.
W Krakowie podpisuje artykuły
Strumenti
i
Przepraszam, to co z tymi grantami, co z
abbiamo utilizzato questo, sì, sì.
to jest EC, to sobie nie przeniesie do...
Ma io comunque.
Tak, bardzo dawno nie widziałem, ale spotkałem się.
I
naciskał, żeby przynieść grafę.
No tak latra.
To tak można powiedzieć.
Comunque dove tu...
Przecież bardzo.
Eh,
Okay, so we are ready to begin the second part of the talk.
sì, sì.
Now,
Voglio come dimostriamo poi.
let me describe some basic properties of this I tuples. So we let IK to be the set of all I2 tuples of X. K tuple just means that it has K many coordinates there. The first one is that if this is a tuple of closed subsets with independence density, positive, then you can find one point inside of each guy so that they form a independent I tuple. The second is that the entropy is positive so long as there exists no diagonal A pair. Yeah, we already saw this one. Yeah, because Banach shows that this happens if and only if there are entropy pairs, and we saw that entropy pairs are the same as non-diagonal IE pairs. This is closed gamma invariant under the action of gamma on the product space, diagonal action. And formally closed gamma invariant the inside of X. The I tuples of these contained in the I tuples of X. This was quite trivial. So the next one. So if we have a factor map, that means gamma also acts on Y, and Y is compact measurable, and this is the surjective gamma equivariant. And continuous. Then you can look at what happens to the I tuples. Then the I tuples of X, you push it down, you get elements, tuples of elements in Y, you get exactly just all the I tuples of Y. The last one, this is a product formula. So when we have actions of gamma on X and on Y, we look at the action of gamma on X times Y, then the I tuples here is exactly the same as I tuples of X times I tuples of Y, precisely equal. Yeah. So here, this one of course is contained in XY to the K. And here, this is containing X to the K. this containing y to the k. Yeah. So the product here is containing x to the k times y to the k. So when we say they are equal, actually we mean that you take the natural identification between these two sets, shuffling the coordinates. So I will explain very briefly the proofs of these ones. They are almost fairly easy, pretty much, and the only technical thing is actually the first one and the last one. Yeah. Then the first one is that I will just say what is the main thing here. The main thing here is for the first part is the following lemma. So if you have the infinite does not intersect in 2, 1, 2, and 3. Then you just say depending only on the size of z, such that for any natural number 1, 2, and s inside of the union with 1, 2. Such that if we look at the map from S to the union with 3, so this map will just, every S here is a map from 1 until N to the union with 1 and 2. What it does is simply just convert the value 1 and 2 into 3. Yeah. So this is surjective. Verify converts 1 to the value 1 to 3. For instance, you see there exists J inside of in here, and J at least Cn. So still part of density, and either. So we get two situations. Either the S restricted to J. Actually, we get everything in with value in Z and 1. Or you get everything with values in Z and 2. The proof of this fact simply just uses this one here. Okay. I'm not going to. The proof uses consequence. Proportionally, Newman uses that lemma. So what it really says is that you have 1 until n here. Now what we're saying is that this S actually is a bunch of maps valued in Z and together with 1 and 2. And when you combine them together into 3, you get everything. Okay. Now we're saying that it's kind of Ramsey phenomenon that now you split this is 3. You can think of the splitting this 3 into 1 and 2. Then you can say the conclusion is that you can get a particle density part J here. This is with particle density, so that on this J, this S actually you still get everything, but possibly with 1 and Z or maybe with 2 and Z, or you get everything here. What you do is simply just use this lemma and do a counting. You see that one of the situation must happen. Then the first part actually will follow from this one. What it really tells us is that so the first part follows from this one. What really happens is that when you have this A1, A2, A3, what you do is that you are assuming that they have particle independence density. So you get independence set there. Then you cut this A1 into 2 pieces. You write it as the union of 2 closed subsets. Okay. Then this lemma will tell us that so if J independence set of A here, and you write A1 as the union of 2 guys. This is A1 1, A1 2, and each of them is still closed. Then you use this lemma, you can get that there exists maybe J prime contained in J, such that the J prime is at least C times the size of J, and this is an independence set for you replace A1 by A1 1, which is AK, or this is an independent set for A1 2, A2, and for AK. But the condition here is that you, for any finite set in the group, you can find one independent set there with a certain density. Then this J prime, together with this condition that you see that it still has a certain particle density there. So you can get that at least one of them has particle independence density. Yeah. Then you do this each time to cut it into pieces. So maybe this one is okay, maybe this one is okay, maybe this one is okay. The next time you cut it further, you see that you still get one piece here, so that they still have particle independence density. Then eventually they shrink to a single point. Yeah, then that is what we're looking for, this I tuples. Questions? Part 3 is quite trivial from the definition. Part 4 also basically trivial from definition. Part 5, if you want to see this is actually contained in here. This is, we just write here. This part is actually trivial, so I can use this one here. So this is trivial. Yeah. For the other direction, what you do is that this is x and y, and this is like y1, y2, y3. So if y1, y2, y3, this is I tuple for y, then you take a very, very tiny neighborhood around them. Then they have a positive independence density. So B1, B2, B3 going on. Then you put back to x, so you get something like this. So this will be pi inverse B1, pi inverse B2, pi inverse B3 going on. Yeah, this is actually just because that they have the same independent sets. Easy to check that. Yeah, then you use part 1 to get that there is one I tuple for x inside of with coordinates inside of these guys. But then their image will be actually inside of these guys. Okay, and that's why I tuple. Okay. So hold on. Maybe I should say something slightly. I should not do this. Okay. Yeah. I should say that you get one tuple in here, but now you can make this neighborhood getting smaller and smaller, shrink into the single points. Then these guys will actually shrink to actually the pre-image of these points. Okay. And for this sequence, you get the limit point because using compactors, you can as the subsequences you can assume that they converge. Okay. But here we saw that the I tuple is actually closed, so you get the limit point is still an I tuple. Yeah, and they actually will be inside of the pre-image of this y1, y2, yk. Yeah, then that is what we're looking for. Questions? Now finally, let me mention the proof of 6. Yeah, so earlier when we defined the I tuples, actually when we defined the independence density, I could have used the lemma for Onst and Weiss to simply say that the limit exists. But we took the trouble to show that the limit is actually equal to the inf. Okay. It will pay off here, okay, in the proof of number 6. Okay. So if you simply use the definition of independence density as a limit, actually you will get a trouble when proving this one. Yeah. So this was proved earlier by Glassner, actually passing to the ergodic theory side, using ergodic theory to prove it. But now we can use the inframed definition of the density to prove it. Okay. So the main thing is this direction. That's the trouble part. The other direction is actually trivial. Right? Just following from like number 5. Yeah. So we look at x1, xk in ik, and y1, yk in y. Okay. So we want to show that x1, y1, xk, yk is an I tuple for x times y. So how do we show this? Well, you just look at some tiny neighborhood of them. So you look at neighborhood aj of xj, bj of yj. Okay, so we very, very small neighborhood. So what we really need to show is that so this will be a neighborhood of this guy will be just a1 times b1. This will be ak times bk. And what we really need to show is that this guy actually has independence density in parity. That's what we need to show. But we already know that because this is a tuple, so we already know that A1 until AK has independence density, say Q1 positive, and B1 until BK also has independence density Q2 positive. We already know that. So now, right here, so you let for NF in gamma, non-infinite. Yeah. First of all, we find J1 inside of F being an independence set for these guys. And we can make the size to be at least Q1 times the size of F. Okay. From the definition of independence density as the infime for the density. Yeah. Now we concentrate on J1. We forget about that J1 is the independence density. We'll concentrate on J1. Look at B here. We see that there is this J2 inside of J1. Independence density for B with this J1 here. J2 would be at least Q2 times J1. Yeah. So then you see that J2 is an independence set for A, also an independence set for B. For both A and B, but then because we're looking at the product action here, then we see immediately that this tells us that J2 is actually an independence set for this tuple. So you get that this one here has independence density being at least this Q1 times Q2 at this part. Order. Questions? So that is, these are the basic properties of my tuples. This will come from the topological entropy. I mentioned there are actually two approaches to the theory. This combinatorial approach. There is also the approach using allegorical theory. You look at the invariant measures. Basically, you have some kind of variation principle there. Then you can look at the invariant measures using algorithm theory for the measure paradigm transformations. Okay. Yeah. So then on the other side, you can pretty much prove everything here. Also using actually on the allegorical series side, yeah, you can also prove number 6 as I mentioned using like an oscillator. And all the other things that can be proved directly, we'll also use them for the entropy pairs. Yeah. Now, but there are also certain variants for the theory. Instead of talking about topological entropy, one can also talk about a certain phenomena actually closely related to it, the sequence entropy. Okay, maybe I should also mention, by the way, that the topological entropy actually is already extended to actions of Sophie groups. for the software groups, actually, you can do a similar theory. Okay. And you can define kind of IE tuples for the actions of software groups. And you can still get that the entropy is positive if and only if there are non-diagonal IE pairs there. Yeah. But then but because the definition of software entropy is quite different, they look quite different. Yeah, then the form of the definition of the IE pairs tuples there is also quite different. Yeah. But the one difference here is that you see the definition of IE tuples tell us that you get this independence density if you define it as infime. Okay. Yeah. You can define it as infime and also as limit along Fourier sequence. For software entropy, for software groups, you cannot define along Fourier set anymore. You cannot define as the limit, but you can define as the infime. Then what happens is that for software groups is that there the IE tuples still has the property that for in the neighborhood they still have for partial independence density. But we don't know what happens to the commas. Okay, so for software entropy, you get two kind of notions of IE tuples. One really characterizes the having partial entropy, and is closely related to the definition of software groups. And the other definition is simply just using this independence density, defined as infime. For that definition, you don't need to use any Fourier sequence, something like that. Okay. Then among the two definitions, the one involving software groups actually implies this definition, but we don't know the commas. Now let me explain a bit what happens to the sequence entropy. There actually, the algorithmic theory approach does not work anymore. Okay, because there you also have a better theoretical version, but you don't have variation principle anymore. Yeah, so then there you really have to use the combinatorial approach. So let me explain what is software entropy, the sequence entropy. So now we're going to take gamma to be countable infinite. And we're going to look at the sequence in gamma. Okay. Yeah. But just for arbitrary group, you don't have a Fourier sequence. Okay, you cannot say okay, like integer group, you take just 1, 2, 3 going on. For general minimal group, you take a Fourier set there. For arbitrary group, you cannot do that. You just take any sequence there. Then Goodman introduced the notion of sequence entropy. It says that, well, you just define pretty much like the topological entropy, except that you just use this sequence to replace in the integer group case 1, 2, 3 going on. You simply take log and joining Sj inverse u equal to 1 until n. So you take the joining of these guys along of u along the elements S1, S2 until Sn. Then you take a limit. But here now you are not guaranteed that the limit will exist, so you can take the limit soup. So that's the definition for the entropy for finite open cover. Okay. Then for the whole system, you can take the supreme over all S, okay, but you can actually also take the supreme over all U. Yeah, I mean, it depends on the choice. You can fix S, then just take a supreme over U. Okay, but you can actually also take a supreme over both. So, This will be taking the supreme over U and S. Then one can try to do the similar thing for this guy, like pretty much like what Banach did for entropy, for the topological entropy. So this was done by Wen Huang, Li, and Song Sao, and Xiaonong Ye, and 3. So they defined the sequence entropy pairs. Similar to entropy pairs. Yeah. So what this really means is that you still have x1, x2, a1. A2 here, you still have U to be the complement of these guys. So now we just require that the entropy for U around some S will be positive when you go over all S. Then it turns out that one can do similar thing for like hyperanalog for IE tuples. Then for IE tuples, we said that what you want is independent sets with particle density. So you can ask what should be the analog here. It turns out that this really just the analog condition here is that you get the arbitrarily large independent set. And tuple. For the distribution like this. Neighborhood xg. 3, for I tuple, what we said is that this guy has positive independence density. Here, now we just say that it has arbitrary large finite independence set. So that simply just means that for n, maybe this independence set. F of A with the size at least questions? Yeah, one can still show that sequence entropy pairs. Is equal to non-diagonal iron pairs. the proof is really the same as what we had earlier for entropy pairs equal to non-diagonal I pairs. Okay. Because what we do.
So I have a question. So for amenable groups, is there any kind of obvious relationship between sequence entropy and the usual entropy?
Yes, so this is larger. This one is larger because in a minimal group, we usually take full set, not the whole sequence. Okay, but like if you think about the integer group, what we usually do is simply just take the sequence 1, 2, 3 going on. Yeah. So if you think, especially think about the integer group, then you for topological entropy you look at the specific sequence. Here we are our arbitrary sequence. So and then you take the supreme, then you get the larger value. Yeah. And for this one you get larger value. Yeah, but for a specific sequence, then maybe you get some smaller value as possible. Maybe.
But are there any conditions under which they are the same?
Not really, but later we'll say that the answer is actually will turn out to be quite clear. I mean, actually it turns out that this one you don't have many choices. Not like for topological entropy, you can get arbitrary value between 0 and infinity. So this one we see that it's always a log of some number, some integer. Okay, that's the result of Huang here. We'll get to that in a minute. Okay. So the proof here, I said, is really the same as what we had earlier for the topological entropy situation. Because there, what we did is simply use the combinatorics or something like that. Look at a fuller set. There you get the part, you get the density, but when the group is, what happens is that here is that I mean, eventually this becomes S1 to Sn becomes very, very large. So when we look at the part of fixed density thing there, you get a very large independent set. Okay. Then basically everything here we said here about I tuples will also be true for n tuples. So I change to n. Then everything here will also be true. With this becomes simply just arbitrary large independent sets. Then we get those, and here the star is positive, only if there are n pairs, and this is still closed invariant, and this will also be true, and this also will be true, but not the last one. Okay. The last one really relies on the definition using inf. Okay, here for the definition of I in there, you don't have inf in there. Yeah, so this one does not work. Maybe it looks like I should almost stop here already. So let me just write down the theorem of I just mentioned Huang and Huang and Xiangdongye showed that actually this is always equal to log n for some n be natural number or maybe infinity. You could get infinity there. Yeah, and where n is simply the supreme of k, where you get a tuple x1 xk, such that these guys are distinct. This is yeah. So So in other words, this n is really the largest length of ion tuples there. But you need to require them to be all different. Because if you get one ion tuple, you can repeat one of the coordinates. You can put the xk, xk, xk there. That's still one ion tuple. Yeah, what is you require them to be really distinct. That's the essential part there. And so, in case that for a minimal group we actually get a particle entropy, then this will actually become infinity automatically. Yeah. So next time we'll see that the proof of this one really essentially depends on this combinatorial lemma. Yeah, but we'll do that next time. Okay, I'll stop here.
Thank you very much. Do we still have any comments or questions?
So the last result, is it for integrals or amenable groups or countable groups?
Can you say that again?
The last result, that one.
This one? This is for arbitrary group.
For?
Any group. Any countable or infinite group. Yeah.
For the IK triple, the entropy of this one is the same as the original distance or any relations?
Same as what? Can you say?
Given the dynamical systems X and the set of IK triple,
Yeah.
it is the subsystems of xk is gamma invariant.
The subsystem of x to the k. Yeah.
Well, do you know the entropy of this?
The entropy of this. You mean talk about IE? You're talking about IE? Okay. Yeah, that's a question. I think the entropy is, yeah, it's actually the same. I mean, this is actually k times the entropy for x, but then that is exactly the entropy for x to the k. Yeah, that's true. Yeah, but I don't think it's in the literature, but that's true. Yeah, that's actually Kazan showed me a proof earlier. Using a Gordic, one has to use a Gordic theory to do that. We cannot. I don't know. We don't know how to use combinatorics to see that.
If there are no more questions, then let us thank Hanfeng again. There was a coffee break, right? And we restarted quarter past.
Io stamattina ho fatto tardi, sottopeso.
Yeah, okay. I find it.
Ah, cazzo della si fa? Non c'è la moca o...
La...
Can I ask you something more?
Ma lì il mio video stavo prima c'era la moca.
Open cover, yeah.
Then the density is a number, right? So then if we take the supremum over covers, I mean the over finite substance, the thing you define, right? So the question is, if we take the supremum over covers,
This is the most one.
density is at most, but it's one for a cover.
I mean, what we can try is, what we said earlier is that for, I mean, a situation like this, x1, x2, xk, you look at a1 for ak, I think what we said is that